Hey guys, in this video I will present the solution to Taiwan Math Olympiad 2023 problem 2. Firstly, we have a look at the statement. We are asked to find all positive integers n such that a, 8 does not divide the number of positive divisors of n, which we will now call d of n, and b, for all integers x to the power of n should be congruent to x modulo n. This problem is heavily inspired by Fermat's little theorem, which exactly states that condition B holds if n is a prime. Furthermore, we notice that for n prime, d of n equals to 2, and 8 does not divide 2, and therefore n prime indeed works. I also want to get the trivial solution out of the way, namely for n is equal to 1, this is a trivial congruence, and furthermore 8 does not divide 1, which is also a number of positive divisors of 1, and hence n equal to 1 also works. When we think about really composite numbers n, I think we, or at least I, get the feeling that a congruence of the form x to the power of s is congruent to x modulo n can really never hold for any s larger than 1, because if x has some divisor, which is also a divisor of n, but it only divides x, for example, once, then any power of x will be divisible by that more than once, and so it feels like this congruence could not hold for larger powers. And when we think about how to formalize this intuition, we can see that the exact problem, the exact case where this problem occurs, is when some square of a prime divides n. So let's assume that p squared divides n, where p is a prime. As I have already said, we want to choose x such that it is divisible by a divisor of n, but only in a low multiplicity. So in this case, let's plug in x is equal to p into b. This tells us that p to the power of n is congruent to p modulo n. We can rewrite this as n divides p to the power of n minus p. And now we want to use the fact that p squared divides n, and therefore by transitivity p squared must also divide p to the power of n minus p. Now we have assumed that p squared divides n for p prime, and so of course n is greater than or equal to 2, and so p squared must divide p to the power of n, and therefore if we subtract that, we get that p squared divides negative p, which is of course a contradiction. Therefore, our assumption was wrong, and we can conclude that n must be square free, namely that no square of a prime can divide n. So we can write n as the product of k distinct primes. Making use of the formula for a number of positive divisors of n, we get that d of n equals 1 plus 1 to the power of k, or 2 to the power of k. By the way, as we always do when we do not go into detail about something in our video, we will put a link to our Wiki entry on our website to the function d of n in the video description. And now we see why condition A was added to the problem, because we are given that 8 should not divide d of n. And since d of n is equal to 2 to the power of k, this implies k less than or equal to 2. Since we have already seen that n is equal to 1 works and n prime always works, the only case we are left to deal with is k is equal to 2. So we can now write n equal to p1, p2, where p1 and p2 are distinct primes. By Fermat's little theorem, we already know very nicely how to work with such an equation modulo p1 or p2. We can use a similar trick as we did here and say that, well, if x to the power of n is congruent to x modulo n, then because p1 divides n, x to the power of n is also congruent to x modulo P1. So let's write this down. We get that x to the power of n, which equals x to the power of P1, P2, is congruent to x modulo P1. Now we want to use Fermat's little theorem, and we will do so only for the case that x is not divisible by P1, because that case is trivial anyways. We will get a 0 congruent to 0, which is not really useful for us. So let's assume that P1 does not divide x, and in this case our equation tells us that x is congruent to x to the power of P1 times P2, which is again congruent to x to the power of P1 minus 1 times P2 times x to the power of P2. Now we know by Fermat's little theorem that x to the power of P1 minus 1 is 1 modulo P1. Taking 1 to the power of P2 is again 1 modulo P1, and so this is congruent to 1 modulo P1. And so we get in total that x is congruent to x to the power of P2 modulo P1. Multiplying with the inverse of x on both sides, modulo P1, we get that 1 is congruent to x to the power of P2 minus 1 modulo P1 for all x not divisible by P1. Recall that we still almost have a free choice for x. So we can just take x to be a primitive root modulo P1. Let's define g to be a primitive root modulo P1. This means by definition that the order of g modulo P1 is equal to P1 minus 1, where the order modulo P1 of some element is the smallest positive exponent, such that this element to this power is again congruent to 1 modulo P1. All of these definitions and statements we use here are also linked to in our description. Now this equation implies, by taking x equal to g, that the order modulo P1 of g divides P2 minus 1, but this is by definition P1 minus 1. This is a really useful conclusion, so we get P1 minus 1 divides P2 minus 1, and because both were defined symmetrically, we get analogously P2 minus 1 divides P1 minus 1. And of course, P1 minus 1 and P2 minus 1 are at least 1, because both are prime numbers, and therefore those two divisibility conditions imply P1 minus 1 equals to P2 minus 1, or P1 is equal to P2. This is a contradiction. We chose P1 and P2 to be distinct prime numbers, which we were allowed to do because we already showed that n must be square free, and therefore we get no solutions in our case k is equal to 2, and so n is equal to 1 and n prime are our only solutions to the problem, and we are done.